If you asked a practicing chemist how he does his calculations for a chemical reaction, most of them would say, well, I create a reaction table in my lab notebook. And that's the way I did it too when I was an industrial or research chemist. And it's funny that we teach the students how to solve it using these one-step, two-step, three-step problems, but this reaction table is very powerful. And so there are occasions, for example, if you want to know everything about everything, well, rather than doing all sorts of conversions, just create a reaction table and it tells you just about everything. I'll show you one and then you go ahead and try to draw one. Well, we're sticking with our reaction of butane here, and this is a balanced chemical equation. And we're solving a problem that says if you're burning 100 grams of butane, how many grams of carbon dioxide can you make? Now you could do a three-step gram-to-gram conversion, and that's probably faster than doing this whole chart. But if they asked all sorts of questions about it, how many grams of everything are involved, this is the way to go. You can do this in any order you want. Most people write the molecular weights for convenience. Now this is not the molecular weight of 2 moles, it's just the data. The molecular weight of a mole of this, a mole of that, which is 32 grams, CO2 is 44 grams, water is 18. We're rounding to the nearest whole number, which is probably not a good idea for most precise calculations, but it gets the job done quickly. They asked us to react 100 grams. So from this single number, the rest of it will all pop out. In fact, it'll tell us how much oxygen we need, how much water we need, none of which were asked, but let's go ahead and do it. I would probably go right to here at this point. We have a little more than half a mole, right? No, I'm sorry. We have a little less than 2 moles. 58 grams is a mole, and we have 100 grams. So I'm going to divide 100 by 58. If you wanted to show it mathematically, do so. But we have 1.72 moles. Then I'd go across here because I have a mole ratio. I need 6.5 times as much oxygen in terms of molecules. That's 11.21. So 1.72 times 6.5 is that. Then look for the easiest conversion. I wouldn't do 13/8. I'd just quadruple this since 2 of these makes 4 of those. And I'd also do 5 times 1.72 for this one. And there's our mole ratios. Now, the amounts. We need 11.21 moles, and 32 grams is a mole. I'm going to multiply. Each mole is 32 grams, and 11.2 of them is 358 grams. Recognizing that this is 458, I better end up with 458 when I'm done. 6.9 moles, where 44 grams is a mole, so I'm going to multiply. I need 303 grams, which, by the way, answers the question, but oh so much more. And it will produce 8.62 moles, or 155 grams of water. This is the big moment where you check it. 458 equals 458. I love it. Everything must be right. That's a reaction table. You could even put molecules down here if you want to add that too. Now, here's one for you. Draw a reaction table for the combustion of 100 grams of magnesium. If you have the printout of this and you want to pause this and do it on your own, fine. When I click, it's going to show everything. And here it is. There's the balancing part, good. And there's our reaction table. The only part you were given was the 100 grams of magnesium. That's a little more than 4 moles, right? 24 grams is a mole. And it requires half as many moles of oxygen, but produces, once again, twice as many, or the same number of magnesium atoms is equivalent to magnesium oxide molecules. I'd then calculate the grams, and I'd do the important check, 165.6, 165.3. We're easily within the experimental error here since we were rounding to whole numbers. And this is molar conversions using the reaction table method.